Alright guys, so in this video we're going to find the pH of bases, so strong bases and weak bases, so you need to know your strong bases for this so that you know which ones are weak. Alright, so remember that strong bases dissociate 100%, right? And to find the pOH you take the negative log of the hydroxide concentration. So we want to find the pH of the following bases, and we also want to find the hydrogen ion concentration and the pOH. And so since this is a strong base, NaOH, it dissociates 100% in water to produce sodium ions and hydroxide ions. And if we have 0.25 molar of sodium hydroxide, it completely dissociates and we get 0.25 molar sodium ions and 0.25 molar of hydroxide ions. And so if we wanted to find the pOH for this, it would simply just be the negative log of the concentration of hydroxide, 0.25, and we would end up getting 0.60. And so then to find the pH is pretty straightforward. It's going to be 14 minus 0.6, and so that's 13.40. So this is pOH, and this is pH. And then for the hydrogen concentration, it'll be 10 to the negative pH, gives me the hydrogen concentration, and so that's going to be 10 to the negative 13.40. And that value is equal to 4.0 times 10 to the negative 14th. And that's the hydrogen ion concentration. All right, and then B. And so guys, what I want to point out before I do B is this pH is really high because this is a strong base. So the pH should be high, not low. Okay, that's acids. And so in B, we have barium hydroxide. And there are two hydroxides there. So I'm going to get barium ions and I'm going to get hydroxide ions. And I'm going to get two hydroxide ions for every single one of these that dissociate. So if I have 3.25 times 10 to the negative third, and this dissociates 100%, I'm going to get 3.25 times 10 to the negative third barium, but I'm going to get 6.50 times 10 to the negative third hydroxide. So I'm just going to multiply this by 2 because it's one of these for every two of these. So the molar ratio is 1 to 2. So that's my hydroxide concentration. So I'm going to find the pOH first because I just have to take the negative log of the hydroxide of the 6.50 times 10 to the negative third, and that will give me 2.187. And then my pH is equal to 14 minus 2.187 because pH plus pOH equals 14. And so my pH is 11.813. And then to find hydrogen, I'm going to take 10 to the negative 11.813. And that would give me 1.54 times 10 to the negative 12. So that's just 10 to the negative pH. All right, and then part C, we have KOH, which is a strong base. So my hydroxide concentration there is going to be 0.050. It's the same as the base because there's only one hydroxide there. And then my pOH is going to be equal to 1.30. And then my pH is going to be equal to 12.70. They have to add up to 14. And then my hydrogen concentration is 10 to the negative pH, and so that's going to be 2.0 times 10 to the negative 13. So weak bases have KBs associated with them. The greater the KB is, the more it dissociates, and the stronger the base. So the higher the pH, right? And if this is my weak base dissociation in water, then my KB expression looks like this. Guys, note there's no H2O here because H2O is a liquid and liquids do not go in equilibrium expressions. All right, now these bases, they look kind of funny. You need to get used to seeing them. So anytime you have a nitrogen in something and it does not have a positive charge on it, it's a base. All right. Okay, so which base has a lower pH? We have 15 molar NH3 ammonia or 1 molar methylamine. So I'm going to look at the Ka's here, but it's going to be kind of hard to tell because they don't have the same concentration. So it'd probably just be easier to find the pH for these. So I'm going to write the equilibrium expression for the dissociation of each of these bases in water. So I'm going to do NH3 first. So I have NH3. I have to react it with water. It's in equilibrium, so I get ammonium and hydroxide. It's a base. It should produce hydroxide, not hydronium. All right, and so my Kb for this, I'm just going to write it down here, is going to be equal to hydroxide times ammonium divided by ammonia. All right, and then for methylamine, methylamine's formula is right here. You are not expected to know that. They would have to provide it to you. And it's going to react with water to produce hydroxide. Okay, so there's the conjugate acid right there. Note, it just attaches the hydrogen to the nitrogen and adds a plus sign. All right, and then the Kb for that is going to be CH3NH3 plus times hydroxide divided by methylamine. Okay, and so to find out which one actually has a lower pH, which means if it has a lower pH, it's a weaker acid. I'm going to look at the rice table. And so I've got 15 molar NH3. Water can be eliminated from this. And this is 0 and this is 0. So then I'm going to plug these values into my Kb. So I would get x times x divided by 15 minus x. And that's going to be equal to 1.8 times 10 to the negative fifth. Now, again, this becomes negligible because these k's are so small, this x is going to be tiny. So if that x is tiny, subtracting a really tiny number from 15 is not going to do any damage to 15. It's still going to be 15 in the end. So we have x squared divided by 15 is equal to 1.8 times 10 to the negative fifth. Multiply both sides by 15 to get rid of that. And then I get x squared is equal to 2.7 times 10 to the negative fourth. And then take the square root of both sides. And x is equal to 0.0164. And then I'm looking at pH. So remember, x here is not hydronium, it's hydroxide, right? So if I take the negative log of this, that's my POH. So the negative log of 0.0164 is equal to 1.78. So that's the POH. And so I subtract that from 14 and I end up getting my pH is equal to 12.22. All right, and then for the methylamine, I'm going to set up a rice table. So I have initially 1.0, get rid of water, none of this and none of that, increasing on this side and decreasing on the left. And then I'm going to plug in all of these equilibrium values into my K. So I'll have x times x right on top. So that's x squared divided by 1 minus x is equal to 4.38 times 10 to the negative fourth. And this x is negligible, like usual. So I end up with x squared is equal to 4.38 times 10 to the negative fourth. And then take the square root of both sides. And my x is 0.0209. And remember, the x is hydroxide. So if I take the negative log of that, I find that the POH is equal to 1.68. And then subtracting from 14, my pH is 12.32. Okay, which base has a lower pH? And that's going to be ammonia. And guys, I mean, look at the difference here. This concentration is so much higher than this one, but still, even though the Kb is so much smaller, it's weaker. So therefore, it's going to have a lower pH. All right. I just wanted to show you that that's true, not just tell you that that's true. So even though This concentration is 15 and this one is 1. So this is 15 times more concentrated. It still has a lower pH. It's still a worse base. All right, it produces less hydroxide because the Kb is so much smaller. All right, another example. So a weak base with a concentration of 0.15 molar was found to have a pH of 10.26. All right, and we want to write the dissociation of the base in water. So it's just a base, so I'm just going to use B, and it's in water, and it's weak, so it's in equilibrium, and we're going to end up making B plus this H, so that's the conjugate acid. You can also write HB plus, I do that half the time too, and hydroxide. All right, so there's the dissociation base. Write the equilibrium expression. Okay, so the equilibrium expression, I'm going to write it over here on the right side. Kb is equal to the concentration of hydroxide times the concentration of the conjugate acid over the concentration of the base, and all those values are at equilibrium. And now we want to find what this is. And so we need these at equilibrium in order to determine that. So I'm going to look at the rice table and see what I can see. So I have 0.15 of this, water doesn't matter, none of this, and none of this. Now, at equilibrium, the pH is this. So that would give me this value here at equilibrium. So I know that the pH is 10.26. Then my pOH is going to be equal to 3.74. And then my hydroxide concentration is going to be equal to 10 to the negative 3.74. And so that value ends up being 1.82 times 10 to the negative 4th. So I'm going to plug that in for equilibrium. And whatever happens to hydroxide has to also happen to the conjugate acid over here because they're both going to be X's, right? And then we have to subtract that amount from here. But if I have 0.15 and I subtract 1.82 times 10 to the negative 4th, it's not really going to do anything to it. Because remember, this number right here is 0.000182. And that's not going to do anything to 0.15. So this is just going to be 0.15. And you can plug it in if you want and see what you get. Okay, but you're going to end up with the same number. So I'm going to take these then, and I'm going to plug them into my equilibrium expression. And I've got 1.82 times 10 to the negative 4th times 1.82 times 10 to the negative 4th divided by 0.15. And I end up getting 2.21 times 10 to the negative 7th. All right, so one thing I want to tell you, you could go ahead and use x's here where you get x, x, and then 0.15 minus x, and plug those into your equilibrium expression. And then determine that x is going to be the hydroxide and plug this in for every single x. You get the same, I mean, it's the same thing. Your rice table is just a little less confusing and more like the other rice tables that you've been doing. All right, so that's it. That's all I have for this. This should be much easier. The only thing you really have to watch out for is that you have to know that your X right here is hydroxide. So if your pH is given to you, you can't just take the 10 to the negative 10.26 because that's going to give you hydrogen. And hydrogen and hydroxide are not the same thing. So just watch for that.